So Yuval, can we start?
Yes, we're now live on YouTube. Yeah.
Okay, so welcome everyone. Welcome to this session on lattice-based and code-based crypto. So, well, just before introducing the moderators, a quick reminder as usual. So please follow the code of conduct, which means in particular that you have to use your real name, and please don't share the link to the webinar. So we have 4 moderators in this session, who are Léo Ducas, Tancred Lepoint, Alex May, and Gilles Zemmour. And so please, Tancred, you can start.
Thank you, Anne. So welcome to the first session of the last day of this virtual Eurocrypt. So this is a session on lattice-based and code-based cryptography. The first talk will be hardness of learning with error on general entropic distribution by Zvika Brakerski and Nico Dotling, and Nico is going to give the talk.
Thanks for the introduction. So, should be in full screen now. Hey everyone, I'm Nico, and in the next 5 minutes or so, I'm going to tell you a bit about hardness of LWE on general entropic distributions, and this is a joint work with Zvika Brakerski. So we all know and love the LWE problem. Let's quickly recap how it looks. You're given a uniformly random matrix A over ZQ and a noisy vector in the row span of this matrix. And your goal is to find the linear combination that leads you there. So one question is, how do you choose this linear combination? In the standard LWE problem, it is just chosen uniformly at random from ZQ to the N. And this error term comes from a short distribution, typically a Gaussian. In this work, we look at the entropic LWE problem, where this uniform distribution of secrets is replaced by an arbitrary entropic distribution. Not quite arbitrary. There, we have to make a requirement that the distribution of secrets S has at least a certain amount of min entropy. And in our work, we will generally think of this distribution S as adversarially chosen. So there have been quite a few works which have looked into this problem of entropic LWE, or in more general LWE with a distribution of secrets that's not distributed uniformly at random. But looking at all these works, you will find that there's one thing in common: the entropic distributions of secrets. Well, here, this first work by Applebaum et al., the distribution of secrets is the same as the error. Goldwasser et al., it's uniform, or it's entropic on 0, 1 to the N. So you will find that all of them could only give security guarantees for LWE or hardness guarantees for LWE if the distribution of secrets was short. So in this work, we first start off with a new characterization of the hardness of entropic LWE in terms of a quantity we call noise lossiness of a distribution of secrets. And this noise lossiness essentially measures how bad of a error correcting code the distributions of secrets is. So not the matrix A, no, the distribution of secrets itself. And assuming that we have hardness of standard LWE, that's LWE with uniform secrets for some dimension K modulus Q and a Gaussian parameter gamma, we get that entropic LWE for a distribution S, for an entropic distribution S is and parameter dimension N, M samples modulus Q, and Gaussian parameter sigma is hard if the noise lossiness is at least K log Q. So the noise lossiness is in effect the quantity that controls the hardness of the entropic LWE problem. So if the noise lossiness is above the threshold k log q, we will get that entropic LWE is hard. And for general distribution, instantiating this with general distributions, we will find that the noise lossiness of sorry, that was not supposed to happen. We find that the noise lossiness of general entropic distributions is the min entropy of the distribution minus this term n log q divided by delta. It's much better for ball-bounded distributions where the noise lossiness kicks in much faster, or in equivalently, the entropy requirements for entropic LWE to be hard are much smaller than for general entropic secrets, which might be an explanation why all prior works looked into distributions of short secrets. Now I'm running out of time. That's why I'm just running over these two slides. But you may ask, the dependency that we get, is it somewhat loose? Can you do better? After all, for general entropic distributions, our entropy requirements are quite high, and the answer is no. We in our work we show that the result is tight up to a n log security parameter amount in entropy. This is supported by matching attacks for specific moduli or moduli that are composites, and a black box impossibility for arbitrary moduli. So to sum up, standard LWE with short secrets tolerates a small amount of leakage, and we do this analysis via a new quantity called noise lossiness. We have matching attacks and black box impossibility results, which essentially show that up to some small slack, our result is optimal. And there's an inherent reason why LWE with short secrets tolerates a much higher leakage rate or much lower entropy in the distribution. That's all. Thanks.
So thank you, Nico, for the presentation. We won't have really time for questions, so maybe the next speaker can go and share its screen. So the next talk is integral matrix gram root and lattice Gaussian sampling without floats. And Young Yu is gonna give the talk.
Okay, thanks for introduction. And I'm going to present our work, integral matrix gram root and lattice Gaussian sampling without floats. This is a joint work with Leo Duca, Stephen Galbraith, and Thomas Pless. This work is about the interaction between two mathematicians, Lagrange and Gauss. Our main result is a lattice Gaussian sampler. Compared with previous algorithms, it does not use floating point arithmetic, and it can achieve a similar quality but with less memory and simpler base samplings. Our techniques are some algorithms for the integral gram decomposition problem. That is, given an integral positive definite matrix sigma, compute some integral matrix A such that AA transpose equals sigma. Actually, this can be viewed as an extension of Lagrange four-square theorem to matrices. Lagrange four-square theorem corresponds to the case n equals 1 and m equals 4. Lattice Gaussian sampling is widely used in lattice crypto systems, including hash and psi, ABE, ABE. In these cases, we need to sample some spherical discrete Gaussians with a good basis. And the packet sampler is a main approach to do lattice Gaussian sampling. It consists of two phases. In the online phase, the sampling is easy, and the most expensive computation can be done in the offline phase. While the online sampling can be fully performed over integers, the offline sampling still heavily relies on floating point arithmetic because it requires to do some continuous Gaussian sampling. And also, it requires to compute some gram root A of the covariance matrix sigma p. And the only suggested way to compute such A is Cholesky decomposition. So A is a square matrix, but of high precision. Because floating point arithmetic has some drawbacks, we want to get rid of it in the whole lattice Gaussian sampling. This is the motivation of this work. And our main idea is to use a rectangle but integral gram root to replace the previous square but real Cholesky root. To this end, we formally studied the problem integral gram decomposition problem, IGDP. The IGDP problem is specified by 4 parameters, where n is the dimension of the matrix, and b is an upper bound of the spectral norm of the matrix. Both a and b are fixed by the lattice crypto system, and d is proportional to the final Gaussian width, and m corresponds to the number of required base samplings. So our goal is to solve IGDP problem for fixed n and b, while keeping d is only slightly larger than b and m relatively small. And to solve IGDP problem, we note that for the case n equals 1, Lagrange 4-square theorem actually provide a solution with m equals 4. And for general case, our idea is to reduce an IGDP instance of large dimension to the one of smaller dimension. This can be expressed as this reduction. By this, we can solve some IGDP instance, but this method requires D much larger than B, which implies a large overhead on the final Gaussian width. So to overcome this issue, we consider another reduction that allows us to reduce the IGDP problem for large matrices to the one for smaller matrices. And with these two reductions, we can compute the integral gram root finally. And the similar idea can be adapted to the ring setting. We generalize the IGDP problems by introducing the ring as a new element. And now we compute an integral gram root over ring. Our discussion focuses on power of 2 cyclotomic ring. Okay. And to solve the ring-based IGDP problem, we need to decompose a single polynomial. And to do so, our method is similar as before. We project the problem onto subring recursively, and this can be written as this reduction. And compared with the generic solution, the ring-based solution achieves a quasi-linear improvement in both storage and running time, but it requires more base samplings. And to conclude, in this work, we formally studied the integral gram decomposition problem, and this can be viewed as an extension of Lagrange 4-square theorem to matrices. As an application, we get a lattice Gaussian sampler that does not use floating point arithmetic. Thank you.
Thank you very much for this talk. So everyone, don't forget to ask questions using the Q&A. Some of them may be answered, but we'll come back to them during the discussion session. So the third talk is when failure is not an option, bootstrapping the search for failures in lattice-based encryption scheme. And Jan-Peter is gonna give the talk.
So, oh no, that's the wrong.
That's the program.
That's the program indeed. So let's see, can you see my screen now? Yes. Okay.
Yeah, it's working.
So hello everybody, I'm Jan-Peter and I will present our work on decryption failures, which is a joint work with Melissa Rossi and Fernando Virlia. So if we look at round 2 proposals in the NIST post-quantum standardization process, and especially at the lattice-based encryption schemes, we see that 7 out of 9 of the schemes are prone to a decryption failure probability. And this decryption failure occurs when an honestly generated ciphertext still fails to decrypt properly. So why would a designer allow such decryption failures? Well, if you allow a certain decryption failure probability, you can scale down your parameters, which means maybe faster communication, maybe faster computation. In general, it means more flexibility. Of course, on the contrary, if your failure probability is too high, this is a security risk. An adversary can collect decryption failures and can use this to retrieve information about the secret. So it's very important to have a good understanding of the attack possibilities of these schemes. Now, I don't have time to go into the details of our methodology, but the online video gives a very nice overview with amazing animations by Melissa. But maybe it's a nice replacement for an evening out to the cinemas in these days. Now, let's immediately go to the results. So a decryption failure attack essentially proceeds in two steps. So first you assemble 100 or 200 failing ciphertexts, and then you use these ciphertexts to reconstruct the secret key. And so the traditional failure boosting approach, essentially the search for these failures is orthogonal. So each time you do the failure, you pay the same amount of work. And so the amount of work goes up linearly with the number of failing ciphertexts that you need. In this work, we show that the information from previous failures that you found gives you some direction of where the secret is. And this can be used to more efficiently search for new failures. And so, as you can see in this on this slide, is essentially the work is dominated by the first failure. So you find the first failure, and then finding subsequent failures is much more, much cheaper. And essentially, you get the rest of the failures for free. And this is the same for the queries. So the number of queries that you need to do through the decryption oracle. So in a single target attack, we can say that the work and the number of queries that you need for this attack is completely dominated by finding the first failure. Now, in a multi-target attack, you have a maximum. So in practical attacks, you can say that, well, we will do a maximum of 2 to the 64 queries you can do to the decapsulation oracle. And one way around this is a multi-target attack. So here you do a maximum of 2 to the 64 queries per target, but you consider 2 to the 64 targets, and you only want to break one of them. And so in this case, you can do, essentially do a very efficient search for the first failure. And then once you find a failure, focus on that one failing target. And then you have to keep on for this 2 to the 64 bound. So the graph that I'm showing you, I should have said earlier, is a toy scheme that we made, which represents Kyber or Saber. It's the same parameter set, or the same has the same properties-ish as Kyber and Saber in this submission. So essentially, in the multi-target attack, the work seems dominated by finding the second decryption failure or finding the follow-up failures in under 2 to the 64 queries. So this is the result of our paper. So in a single target attack, an adversary should not be able to find one decryption failure with high probability and with less than 2 to the 64 queries. In a multi-target attack, finding one decryption failure is not devastating, but finding the follow-up failures in less than 2 to the 64 queries dominates the concept. And I want to stress that no NIST post-quantum round 2 scheme was broken by our paper. So possible future work is applying this failure boosting framework to LWE schemes with error correction, or just to any encryption scheme with decryption failure possibilities, because it's a general framework. And a possible other thing is to fine-tune this multi-target attacks to get a few even more bits faster in this attack. So thank you for your attention.
Thank you very much, Jan-Peter. So if we don't have questions yet for you, so maybe we can go to the next presentation. So the next talk is key recovery from Gram-Schmidt norm leakage in Asch-Ensign signature over n-true lattices. And Young-Yu is gonna give the talk.
Okay, thanks again. And I'm going to present another work, key recovery from Gram-Schmidt norm leakage in hash and size signatures over n-true lattices. This is a joint work with Piana Fook, Paul Kirchner, Mediki Buch, and Alexander Wally. This work is about cryptanalysis. Our targets are two lattice hash and size signature scheme, Falcon and DLP. In this work, we identify a source of side channel leakage in some implementations of Falcon and DLP, and we also studied the link between this side channel leakage and the secret key. Falcon is a strong round 2 candidate in the NIST PQC competition, and DLP is the ancestor of FECN. Both FECN and DLP are the instantiations of GPV hash and psi over entry lattices. For a GPV hash and psi scheme, the signing algorithm consists in lattice Gaussian sampling. And when it is over entry lattices, the sampling basis, or the trapdoor basis, is the entry basis, in which 4 elements are short polynomials, and the G and F are the entry secret key. In FECN and DLP, the lattice Gaussian sampling is accomplished by the KGPV sampler or its FFT variant, in which the high-dimensional lattice Gaussian sampling is decomposed into many one-dimensional integer Gaussian sampling, and the standard deviations of those integer Gaussians are inversely proportional to the Gram-Schmidt norm of the trapdoor basis. And in some implementations, the integer Gaussian sampling is not constant time due to the different Gaussian parameter. And we show that the timing leakage, the timing information would leak the information of the Gram-Schmidt norms. We call this leakage Gram-Schmidt norm leakage. And in this work, we show that Gram-Schmidt norm leakage is dangerous. We first propose a polynomial time algorithm to compute the entry secret key F and G from all the Gram-Schmidt norms of the untrue trapdoor basis. Our algorithm consists of 2 steps. At the first step, we compute a polynomial FF bar plus GG bar from the Gram-Schmidt norms. Here, the bar denotes the complex conjugation. And once we compute FF bar plus GG bar, then we can compute the entry secret key F and G from it. And the second step is polynomial time, because it is based on the famous Gentry-Sealer algorithm. And the first step is our main technical result. And in this work, we propose 2 different polynomial time algorithms for FECN and DLP to compute FF bar plus GG bar. That is because FECN and DLP use different matrix form to represent polynomials. But this algorithm is theoretical because it supposes exact Gram-Schmidt norms are provided. However, in practice, we must take into account the major error on the Gram-Schmidt norm leakage. And for the case of DLP, we can indeed adapt the previous algorithm to the noisy input, and we validate it experimentally. To deal with the noise on the Gram-Schmidt norms, we combine the previous algorithms with tree search, and our experiment result shows that with about 2 to the 35 DLP signatures, we can break some concrete instance in practice. Unfortunately, for the case of FECN, dealing with the noisy input remains open. We have not get the solution. Okay, to conclude, in this work, we formally we studied the side channel security of FECN and DLP. We show that in some implementations, the Gram-Schmidt norms of secret basis leak through timing. And we also show that the leakage is dangerous. We propose a polynomial time to compute the entry secret key from the Gram-Schmidt norms of the entry secret basis. And based on that, we propose an experimentally validated attack against the DLP. And this can also be viewed as an evidence of some weakness of all the implementation of FECN. And at last, we should highlight that in the updated version of FECN, the Gram-Schmidt norm leakage has been well patched. While the countermeasure would lead to some efficiency loss, our result shows that the countermeasure is important for security indeed. That is my talk. Thank you.
Thank you, Yang. So the next talk is an algebraic attack on rank metric code-based crypto system, and Magali Bardet is going to give the talk.
So this is the code-based part of the session. And this is a joint work with Pierre Briot, Maxime Brosse, Philippe Gabory, Vincent Neger, Olivier Ruata, and Jean-Pierre Tillich. So we are analyzing the Machilis crypto system that is as old as the RSA crypto system. The first systems were using the Hamming metric, but the problem is that it generates a huge public keys. And recently, a new metric appeared, the rank metric, and we can use coding, error correcting code in rank metric. The main benefit is that it generates shorter public keys when we use particular linear codes in rank metric that are called FQ2ZM linear codes. And we are mainly interested in those kind of codes because there are actually two submissions in the second round of the post-quantum NIST competition that are RORO and RQC. RORO is an analog of the N-true crypto system. It uses LRPC codes that are analogs of LDPC codes, but using rank metric. And for RQC, there is a security proof that relies the security of RQC to the decoding problem in rank metric. So we want to analyze the security of the decoding problem in rank metric. And this problem is a hard problem. There is a randomized reduction from the decoding problem in Hamming metric that is known to be NP-hard to the rank decoding problem for FQ2ZM linear codes. So this is a hard problem. Up to now, the parameters in the NIST proposal were based on combinatorial attacks that were the best known attacks. And the costs, if we have a family of linear codes over F2ZN of length n and dimension n over 2, and we want to correct an error of weight r, then the cost is 2 to the r times n. And we will see that using algebraic attacks, we can do much better than this. So I will try to summarize our results. We started from the algebraic modeling from Urilski and Johansson in 2002. So they wrote an algebraic system. I will not detail here where does it come, but the green part are known values. There are matrices, and the S and C are two matrices whose coefficients are the unknowns, the variables of the system. So we want to solve this system and find the values of S and C. And so there are a certain number of equations and variables, and we have usually much more equations and variables. So we hope we can solve this system. There are many solutions, but with some specialization, we can reduce to the case where this system has only one solution. In 2006, Levy, DVL, and Perret started to solve this system with Grabner-Basis computation. And recently, a paper from Verbel and Hall in 2019, studying the min rank problem, which is very close to this problem, shows that when you compute a Grabner basis, so usually the strategy goes by increasing degrees, and in degree r+1, something happens. There are many degree faults in the computation, and experimentally, we see that for good cases, there are so many degree faults that the computation stops in this degree. So what we did in this paper is that we identify exactly the degree fault in degree r+1. And more precisely, we computed theoretically the result the resulting polynomials of degree R that are produced after this degree fold. So this is the set of polynomial we get. There are equation of degree R, and there are maximal minors of a particular matrix that is here in the original system. And you can see that only one part of the variables are used in these equations. Instead of computing the global basis up to degree R+1, we just need to compute this equation. The cost is very small, just the size of the equations. And we get at the same step of the computation than after the first degree fold here, but with much less computation. The second contribution is that if we look at those equations, then we yes.
We don't have much time left, so if you could.
Okay, so it's almost the last slide. So we can solve using a change of variable, and in the good cases, we show that linearizing the variables, linearizing the equations here gives the solution. And for a family of code like that, the complexity analysis gives us 2 to the R times log n instead of 2 to the R times n for the combinatorial attacks. So this is the result in the paper for the ROLO and RQC crypto systems. So we have a better result than the combinatorial attacks, and so we improved the result since the submission of the paper, and we have very good complexities that completely breaks the proposed parameters. And so to conclude, we had a much more precise analysis of the complexity of this attack, and now we are able to propose new parameters, taking into account the new complexity. So we have to increase R by 2, and it increases the size of the public key, but it still gives an attractive size. So I'm done. Thank you for your attention.
Thank you for the presentation. So the next talk is key homomorphic pseudo-random function from learning with error with small modulus. And Sam Kim is going to give the talk.
All right, so thank you very much. So my name is Sam, and I'll be talking about key homomorphic pseudo-random functions from LW with a small modulus. So, so the topic of this talk is on pseudo-random functions, which I assume most of you are already familiar with. So these are just deterministic functions that are computationally indistinguishable from a random uniformly generated function. So pseudo-random functions are very useful objects in cryptography. You know, they're really a workhorse in symmetric crypto, so they can be used for like symmetric encryption or MAX. And even beyond symmetric crypto, you know, they're useful for a variety of protocols. So if you want to like de-randomize some randomized algorithm, or PRFs are very useful if you want to get more random bits, then PRFs are also very useful in those settings. So PRFs are very important objects in cryptography. So in terms of constructions, we know a number of ways on how we can construct PRFs. So we can first use block cipher design principles to design block ciphers that can be modeled as a secure PRF. So for instance, AES is generally modeled as a secure PRF, or I guess in this case, a pseudo-random permutation or a PRP. We can also construct PRFs that are provably secure, starting from specific algebraic assumptions. So there's a number of ways. There are a number of ways that we can do this. For this talk, I will focus on lattice-based PRF. So let's directly head into the world of lattices. So I guess in the world of lattices, there are two main families of PRFs that we generally study. So the first family is the GGM-based PRFs. So these are PRFs that follow the classical paradigm of Goldwasser-Macaulay from '84. And so this paradigm allows us to start from any one-way function and construct and transform it into a secure PRF. So we can instantiate the one-way function from any hard lattice problems like short integer solution problem or the learning with errors problem. And the resulting constructions in this family are very simple and quite elegant, which is a big plus. But at the same time, these constructions don't necessarily give you the most concretely efficient constructions. And the constructions themselves are also inherently sequential. So this means that in order to evaluate the PRF, you need deep evaluation circuits, which is not ideal if you want to have some like hardware acceleration, which is important for like fundamental primitives like PRFs. So the second family of PRFs are the direct PRF constructions from LWE. And these constructions tend to have better concrete efficiency. They also have shallow evaluation circuits that are also very nice. And they also have like additional algebraic structures like key homomorphism, which are very useful for applications, which I'll refer to the paper for the details on these properties. But these second family of PRFs also have a one downside, and this is the reliance on LWE with a superpolynomial modulus Q. So I won't go into all the details in this talk, but basically the modulus Q that I'm referring to is the modulus Q that's associated with the traditional LWE assumption, LWE problem. And basically, if you have a bigger modulus Q, then the PRF that relies on this LWE assumption have to work over a bigger ring or bigger field. So the operations of the PRF become slower. And also the modulus Q impacts the quality of the assumption of the LWE. So if you have a PRF that relies on LWE with superpolynomial modulus Q, then it's making, then the PRF is relying on a much stronger assumption than compared to LWE with just a polynomial modulus Q. So basically, I guess prior to this work, basically all non-GGM based lattice PRFs relied on LWE with a superpolynomial modulus Q in the security parameter. So the open problem that we tackle in this work is basically constructing an LWE based PRF that with only a polynomial modulus Q in the security parameter. So let me just state our result and conclude. And so we basically give two constructions in this work. The first construction, we focused on constructing a low depth PRF, relying only on polynomial modulus Q. And so our PRF can be evaluated in NC2 circuits. And our second construction, we construct key homomorphic PRFs with a polynomial modulus Q. And all of our constructions can be extended to the ring setting as well. And the main technique that we use is what's called chaining, which I think may have applications even beyond the context of PRFs. Okay, and that's it. Thank you very much.
Thank you very much, Sam. So the final talk of the session is Black Box Secret Sharing Revisited, a coding theoretic approach with application to expansionless near threshold scheme. And Ronald is gonna give the talk.
I have a problem with my Can you see something?
Yeah, it's working now.
Okay. Okay, let me start. So this is it's my presentation of my work with Xiaoping Xing on Black Box Secret Sharing Revisited. I'm going to quickly overview the result, and I'm going to quickly sketch our approach, but I'm going to choose a slightly different yet alternative version compared to what we did in the paper. So first of all, let me describe what is a black box secret sharing to you. So we have a TRN secret sharing scheme given an arbitrary finite abelian group G. There are n players. The dealer has a secret S in the group G, and each share Si is a number of Z linear combinations of the secret and random coins in the group. Reconstruction is by Z linear combination over R shares given the secret. Privacy, T shares Si give no information on the secret, and now the black box crucial point is that the Z coefficients in these combinations do not depend on the group. So if you operate this type of scheme, it only requires black box access to group. So like representing elements, selecting randomness, and performing group operations. So applications of this started 30 years ago with threshold RSA. It was first introduced by Desmet and Frankel. Now, the expansion in a black box secret sharing scheme is the average length over the number of players of a share when viewed as a vector. So each player gets a number of elements, and the length of that as a vector is the expansion. Now, the known results here, from my work with Veer from 2002 crypto and with Veer and Stam from crypto 2005 is if you have T and N and T is at least one and smaller than N-1, then there is a threshold black box secret sharing scheme with privacy T that has expansion log N. So there is a price for threshold black box secret sharing, but one can show that this is optimal. In fact, it follows from known bounds on linear secret sharing over fields, putting the group G equals Z over 2Z in the definition. Of course, we exclude the cases T equals 0 and N-1, because there we have trivial solutions without expansion. T equals 0 is just giving your secret away, and T equals N-1 in the threshold case is just additive N out of N secret sharing. So you have to exclude the extremes here. Now, how are these results proved? So it works over number fields, suitable number fields. You take a suitable number field K, you take its ring of integers, and you tensor that over Z with the group G. And that is a finite module over OK that you can perform with black box access to G. Now, what you need is that OK contains a set U that is exponential in size in the degree of the number field, and that set defines a van der Monde determinant that is primitive in the number field. It means it sits in the ring of integers, and it's only rational primes that divide it are plus and minus 1. And such number fields can be carefully constructed. See Crypto 2005. But here we're going to do other stuff. So now I present our main result, expansionless near threshold black box secret sharing. So we show in the paper here at Eurocrypt that there's a family of TRM black box secret sharing schemes for any number of players and for privacy parameter, at least one smaller than N-1, so the interesting case, with constants as follows. Constant expansion, so not logarithmic, constant. An arbitrary privacy rate T over N and an arbitrarily small reconstruction gap rate R minus T divided by N. Yeah, and we also show using known bounds that this is optimal. So you see that if you tolerate an arbitrarily small gap between a linear gap, but arbitrarily small between privacy and reconstruction, you go from logarithmic expansion to constant expansion. Possible applications here are class group cryptography and also some threshold RSA application that we described briefly in the paper. And our approach here is not number theoretical, but it's coding theory over the integers, over FQ, over Z modulo P to the UZ, and then we use algebraic geometry codes. And we also show that the result we obtain here cannot be achieved by our previous methods. So how does this work? Very briefly, 2 slides. So first we introduce lambda weak black box secret sharing. That's the same as before, except you only secret share a lambda multiple of the secret, and you reconstruct a lambda squared multiple of the secret. Now we have a simple lemma that if we have 2 weak secret sharing schemes, one lambda, one mu, and lambda and mu are co-prime, then we can combine the 2 secret sharing schemes independent. And just using the fact that lambda and mu have greatest common divisor 1, we can combine it trivially into a black box secret sharing scheme with the same privacy and reconstruction parameters. So that's you should keep in mind. Now we introduce a folded integer code, an IC. So an n, L IC is simply a Z linear subspace of Z to the L n copies of that, and it has dimension k. So note that the dimension is very well defined because of structure theory of modules over principal ideal domains. These things always have a dimension and also a basis. So my code here has length n, but it's over alphabet set to the L. And now we get the first main result we get is a reduction theorem for weak black box secret sharing. So M is now a length n, dimension k, integer code over alphabet set to the L. P is a set of rational positive primes, and A and B are positive constants. Now, if we have that for each prime in the set P, it holds that reduction modulo P gives an L-folded FP linear code of dimension k, 1, and 2, the distance of this code is always at least A, and the dual distance is always at least B. Then we show that there is a lambda weak TRN black box secret sharing scheme with expansion L, so that, very important, lambda has no divisor in this set of primes P. The privacy threshold is at least P minus 2, and the reconstruction threshold is at most n minus A plus 2. Now, the proof of this result is...
We're out of time. Could you please conclude so we have time for questions?
Yeah, the proof of this result does not look into codes modulo P to the U, but it's implied by the conditions. And so what we do is we construct two schemes, one for a finite set of primes, one for an infinite set of primes. The last thing is based on Shamir secret sharing over the integers. The finite part is by using FP linear folded FP linear codes with suitable parameters, Chinese remaindering them together and lifting them arbitrarily to a Z matrix. And to make this all work, we get a non-trivial AG code analysis because it has to work for all lengths n. Parameters have to match. You need flexible nearest threshold and constant folding. So that's actually quite delicate analysis. But this concludes the basic overview of our approach in an alternative version compared to the paper.
Thank you very much.
Okay, so maybe I take over for the questions and answers. So we had a very active session. That's very good. Lots of questions, and I try to repeat some of them because they may be interesting for a broader audience. And maybe we stay in line of the talk. So maybe we start with Nico first. So there's two questions for Nico. So at least two. Let's see. There was one by Scott Flora, who was asking whether there are usable distributions, usable in the sense that you can use it in crypto primitives with better security than the standard uniform small distribution. Nico.
Yeah, so one very popular example is to use the same distribution as the noise distribution. And for some crypto systems, like the provably secure N-true crypto system of Steele and Steinfeld, you actually have to do that. So using the same distribution as the noise distribution is actually something quite common.
Okay, and the second question is, can you extend your results to the ring setting?
So not immediately. The results that we have in this work don't immediately translate to the ring setting, but we are working on some follow-up using slightly different techniques.
Oh, good to see. Thank you very much. So a question to Yang's talk. So this was the second talk, and there was a question, what is the meaning of similar quality? On your slides, you didn't properly define what similar quality of the sampler, I think, meant. Can you say something, Yang?
Okay. Actually, the quality of the sampler is the minimal Gaussian width it can achieve. And for the original Cactus sampler, this value is about the singular value of the sampling basis B times a smoothie parameter. And in our sampler, we only increase the quality by a factor of 1 plus small o1. So we think that is similar. And that would not affect the parameter in practice crypto system.
I see. Thank you very much. So maybe over to the third talk. So there was a question posed in the Sulip chat by Leo Ducat, who was wondering whether your analysis, Jan-Peter, also applies to multi-target attacks of any of the NIST schemes. And there's a follow-up. Do you have a method to circumvent the multi-target countermeasures?
So it's an interesting question. So the framework itself holds for any of the NIST lattice-based schemes, of course. The analysis itself, it's more complicated to port them. So we really need to be careful. We made a lot of assumptions which are valid for the scheme that we researched, but I don't know if we can just port it. So there's more research needed to really do the analysis itself for the different schemes, especially the compression of the ciphertext, which is the term G in the paper, I think we need to be careful to just.
Can I interrupt, because I think you've misunderstood my question.
Okay, yeah.
When you speak of multi-target attack, you mean attacking different public keys, right?
Yes, yes.
Yes, so there are techniques in the NIST schemes so that you cannot use the same ciphertext for different public keys. Do you have a countermeasure? Do you have a way to avoid that?
No, we don't
assume that this is not applied.
No. We assume so there is two different multi-target attacks that you can talk about. The first one is essentially there's no multi-target protection, so you can generate a weak seed and essentially use that for any of the public keys. So that's one, and you can really easily, as Kyber does, as most of this submission I hope do now, you can really easily stop that by introducing the public key essentially at the start of the ciphertext generation.
Okay.
So we're not talking about that. So in our paper, we're looking at multi-target attacks where this protection is already in place. And the only thing that you actually gain is that essentially for the first ciphertext, you gain a lot more space for looking. So you get more space for looking at the first ciphertext. But once you find this first ciphertext for a certain failure, you just go for that target. And then essentially, you just have the same problem, only you have already one hint.
Okay,
so that's
get it. Thank you.
Okay.
So thank you very much. And then we come to the fourth talk. It's again Jan. So there was a question about your experimental results. You said that you can break DLP, and I think the question was up to which dimension?
And the parameter set we consider is claimed for 192 bits of security, in which the degree of the untrue ring is 2 to the 9. So the dimension of the lattice is 2n is 2 to the 10.
I see. Okay. And there was another question about the hardness of Lagrange's four-square theorem to matrices. So the question is it harder or easier than those problems that we are more familiar with?
The question, I think the question is about the Gaussian sampling work, right?
I guess so.
And actually, the IGDP problem, the integral gram decomposition problem, is easy. Actually, we propose some efficient algorithm to solve it. This is our contribution.
All right, so let's head for the fifth talk by Magali. And there's a question about, so not in your short talk now, but in your extended talk, you mentioned a signature scheme, Durandal. And the question is, does your attack affect this scheme as well?
That's a good question. I didn't try to compute the complexity of the attack and the Durandal scheme. And so it's based on the wrong syndrome decoding problem. So maybe the attack can have an effect, but I don't know if it's better than the combinatorial attacks or the other attacks.
I see. Okay. Good. And maybe a question to Sam's talk. So there's a question whether your small modulus technique extends to LPN, and if not, do you foresee any promising alternative methods for LPN?
Yeah, so I guess our technique works with the assumption that there is some rounding function. So I wasn't able to talk about it in the talk, but all the all the lattice-based PRF functions depend on this operation called a rounding, which maps ZQ elements to ZP. And I guess in the LPN setting, there isn't really like a good analog for this rounding function. So you can think about like natural ways how we can go about this. Like for instance, you can take vectors in Z2 to the n and then map it to some like nearby code words for some code. All that is guaranteed by codes is that if you start from a code word and if you add error to it, then you can map it back into the code word. But it doesn't guarantee that if you map like uniformly random into this Z2 to the n space, then you can't like, it doesn't allow you to decode into like a code word. So I guess our method in the paper works assuming that there is a rounding function. And so I think, so it's not really clear how to apply it to the LPN setting, given that there is no rounding function in the setting. Yeah.
I mean, there exists a rounding function for codes. It's called quantization, huh? Or source coding.
Oh, so what is this called?
Quantization or source coding.
Oh, I see. Yeah, so I'm not familiar with that, but maybe that's a nice open problem to look into. Yeah.
I see. So thank you very much for answering these questions. So are there any more questions to the speakers?
I think there is one question for Ronald in the Zulip chat.
I see.
From Abbas Sheragi, who is curious about the construction of the field that Ronald mentioned needs some care. What is important in the construction of those fields?
Yeah, in these older works, in order to get to emulate somehow Shamir secret sharing scheme over defined over OK tensor G, you need that this ring of integers of the number field contains a sort of a special set. You would like them to be such that the differences of the elements are units, but that doesn't work quite well because in number theory, we know only to get such a set in cardinality order of the degree of the number field, and we need it to be exponential. So the older results, they work with a relaxed notion, not that the differences are units, but that the product of the differences is primitive. And then actually you can pull off a version of Shamir secret sharing. So, but you have to design your number field very carefully using a mix of number theory and geometry to ensure that such an exponentially large set is contained. Now, I can also say that it's for this reason, the older methods are really sort of van der Monde based, and these newer results about near threshold with constant expansion, they're not at all so much based on van der Monde type of technique. So the old results don't carry over, or the methods do not have much bearing on this new setting. And actually in the paper, we argue that it would not work.
Thank you. I think Yongyu wanted to ask another question. Do we have time?
Yes, we have some time.
I want to ask a question about the decryption failure paper. And because the failing ciphertext should be related because it depends on the previous ciphertext. And I want to know, how does the correlation affect the lattice reduction for key recovery later?
Interesting question. So yeah, there is indeed a correlation between failing ciphertext that you find. We assumed that the correlation is not too strong because we're in a very high dimensional space, and due to this high dimensional space, essentially ciphertexts are pushed towards orthogonality. but this is certainly something that also needs to be, taken into account. And we did the assumption that there is no dependency there or correlation there. So this is very interesting. Also something to follow up.
Okay, thanks.
Are there more questions? If this is not the case, then this is time to thank all the speakers. I very much enjoyed the session. And I think it was great to have you virtually here, but it will be also great to see you all back in real life again. I hope this will be soon. Okay.
Thank you.
All right.
Thanks
Thank
all
you.
of you. And
Bye.
the next session will start in 15 minutes. Thank you.